So let's look at pressure in an ideal gas. Imagine there is a tank of rectangular shape, okay? It's got 3 dimensions, A, B, and C. It is filled with ideal gas. Here is a typical gas molecule. This gas molecule can collide with each of the 6 faces. We're only interested in this surface, okay? B and C, and that is parallel to the YZ plane. Okay, so the only reason why a molecule can collide with it is that this molecule comes in with a velocity along the x direction. Okay, if there is no component of velocity along the x direction, this molecule will only move parallel to the plane, will never hit it. Okay, so here is a typical collision, like this. Okay, let's assume that the collision is elastic. So you see, we're looking at the microscopic property now. Okay, we have to know the mass of that molecule. Okay, we have to know its speed, and we also have to know the nature of the collision with the wall, and we assume it's to be elastic. So all these are microscopic property. That is what we start with in a statistical mechanics problem. We start with the molecular nature, and let's see how this results to lead to something macroscopic such as pressure. The idea is this: the reason why this surface experiences the pressure is because of all these collisions by all these molecules with this wall, right? Each collision gives a tiny, tiny impact. You're probably not going to notice, you won't notice at all. A tiny, tiny impact. Because there are so many such collisions, some violent, some less violent, some soft, and so on. On average, there will be a certain amount of force exerted on this surface, and we divide by the area, we get what's called pressure. Okay, so let's look at the typical collision. Okay, now, since this is an elastic collision, and it is colliding with a wall which is parallel, which is perpendicular to the x-axis, right? Perpendicular to the x-axis. So only the x component of the momentum gets reversed, right? It comes in this way and comes out that way. What about the y and z? Well, they don't change at all. So I'm not going to worry about the change in momentum in the y-z direction, just the change in momentum in the x direction. It comes in with a momentum. All right, it comes in with a momentum in the x direction. What is that equal to? That would be mv sub x. Okay, coming this way. It comes out in the x direction with the same amount of momentum, except vx is now reversed in direction. It is reversed. So what is the total change in momentum in the x direction? What is delta px? What's that equal to? That p is momentum, not pressure. Okay, that would be mvx minus, okay, I'm assuming that after the collision, I'm assuming this to be the positive direction, okay, for simplicity. This to be the positive direction. So after the collision, the momentum is mvx, but before the collision, it's negative mvx, because before the collision moves that way. Okay, so that is 2 mvx. That is the change in momentum for this one molecule. And what does that come from? According to the impulse momentum theorem from Newton's second law, remember? Okay, the reason why there is such a change in momentum is because this molecule suffers a force, okay, from the wall. And that force, of course, is what we're looking for. Because when a molecule gets a force from the wall, it also gives the same magnitude of force to the wall, and that's where the pressure comes from. Now, this is only one collision, and this molecule will go forward and hit that wall and bounce back, right? So it comes in like this, like this, like this. If you look at how the momentum changes, if you look at the collision event, okay, look at the collision event from this one molecule, it will look like this. There's a collision, there's another collision, there's another collision, there's another collision, so on. So the force given by this molecule on this wall is not a constant at all over time. Rather, there is a sudden force and then zero from here to there. That's when the molecule is not in contact with the wall, and then bounce back another collision, and then bounce back another collision, and so forth. Okay, the impulse is tiny, and this distance is also very short, and therefore we're interested in some sort of average value. Okay, we're interested in this average value. And how do we do that? Well, all we have to do is to realize that it takes a given amount of time for this thing to come back, and once it comes back, it does this again. Okay, so the time duration between two successive collisions, delta t, is what we're looking for. Delta t, what is that equal to? Okay, now, for this thing to come back, it must move to this wall and come back again. This has to do only with its x movement. Okay, I don't care whether it makes a movement in y direction, z direction, or even make a collision with other walls. It doesn't really matter. But for this thing to come back, I only have to focus on x movement along the x direction. Okay, the distance it has to travel before coming back is twice the distance a, so it's 2a. And you have to divide this by the speed of this molecule. Now the speed never changes because remember this is elastic collision. Okay, it doesn't change the speed, only change the direction of motion. That's Vx. Okay, so over time delta t, what is the average rate at which the momentum of this molecule changes? That would be delta px over delta t, right? The rate of momentum change. Okay, delta p over delta t. And what is that equal to? That is equal to, I'm plugging in this, okay, 2mvx divided by 2a over vx. Okay, let me simplify that. That will be mvx squared over a. Okay, this is the contribution to the collision force from this tiny molecule. Of course, we're not interested in just one molecule. We're interested in all these molecules together, and therefore we need to add everything up. Suppose we have all these molecules. This is only one molecule. Let's call it this is the ith molecule. Okay, so the total force exerted on this wall, F, due to all these molecules, I must sum over all these molecules. Each molecule is, I use a subscript I to denote this is mi vix. This is the x component of ith molecule speed divided by a, right? All right. Now, this is the force exerted on the wall. This is the force exerted on the wall perpendicular to the x direction. How do I find the pressure? Okay, let's take this back. Okay, the force exerted on this wall, right? How do I get the pressure? I have to divide this by the area of this wall, right? Area of this wall, which is B times C. Okay, so what I'm going to do is I'm going to divide this by B times C. This will give me the pressure exerted on this wall, P. So, B and C. So you have A, B, and C. What's A, B, and C? A times B times C. Isn't that the volume, right? Isn't that the volume of this box? So that's 1 over V, volume. Mi Vix squared. All right, there we go. Now, take a good look at this expression. For simplicity, I'm assuming that the masses are the same, okay? So m sub I don't have to use I anymore because every mass, the mass of each molecule is just the same. So I can simplify this as m, that's the mass of each molecule, over V. And then the sum of Vix squared. Okay, now you are adding all these terms up for each molecule, right? Isn't this equal to, okay, here comes the key here, the average value times n, the total number of molecules? Because this is how we define the average value, right? We add every term up, we divide it by n, right? That you get the average. Then multiply by n, of course, you get that. Okay. Going from here to there allows us to relate the average value of a molecular quantity, in this case, the average value of the x component of the velocity squared of each molecule, with the macroscopic quantity in question, and that is the pressure. Okay, now, of course, that's not the end of the story. We must figure out this somehow, right? You notice that there is an x component here. That's kind of weird because what's so different about x? Why is it so different from y and z? Why do we have to single out x? Well, the answer is clear when you go back to this diagram here. The reason why x is singled out is because we're interested in this wall, right? The pressure on this wall. And the pressure on this wall is due to the fact that the molecules are coming in along the x direction and bouncing back along the negative x direction. That is why we single out x. But in reality, the pressure should be the same among all 6 walls, right? It doesn't really matter whether you use X and Y or Z. As a matter of fact, what that tells us is that if I replace this with Y instead of X and replace with Z, I should get the same average value, right? Because on average, the molecules do not have a preference whether it wants to move along the X direction, Y direction, and Z direction, because the motion is completely random. Okay. Now, this, of course, is an assumption. It's called a statistical assumption. But when you look at a very large number of molecules, this certainly makes sense. Okay. That is, because the motion is totally random, each molecule does not have a preference whether it favors the X direction, Y direction, Z direction. Therefore, according to this assumption, I can replace with Y and replace with Z and get the same value. Okay. In other words, I can say this is mn over v. I can say this is vix squared, but also viy squared and viz squared. These 3 values are all equal to each other. But of course, I just basically added 2 identical terms to that. I must divide it by 3. Reason why I do this is because now I introduced not just x but y and z to make it symmetrical about x, y, and z. Okay, but you notice that if I did this, this is vix squared, viy squared, viz squared. This is not any power; it's the second power. Okay, now if you add 3 components squared, what do you get? According to Pythagorean theorem, okay, this is just so nice because it's squared, not just anything else. This is just vi squared. That's it. Okay? It is not just vix anymore, just vi squared. Now, take a good look at this. I have the mass of each molecule. I have the speed average. You combine mass and speed squared. What does that remind you? Doesn't it remind you of something similar? It's very familiar called kinetic energy, right? Now, if I then single this out, mvi squared, right? Of course, the kinetic energy also has a 1/2, right? 1/2 in front of it. So what I need to do is I multiply this by 2 to cancel with that 2. And don't forget there's mn over 3v. Actually, m is gone. 2n over 3v. Okay, now this thing in the parentheses, this is just the average kinetic energy of each molecule. So this is 2n over 3v times k average. Okay, now isn't that nice? This tells us that there is an explicit connection between molecular quantities and macroscopic quantities. The pressure of a tank of ideal gas is directly proportional to a molecular property, and that is, what is the average kinetic energy of each molecule? That's k bar. That's what k bar means. This is a beautiful example of how statistical mechanics works. See, basically what we did was we started from the molecular behavior, right? Elastic collision between the wall and so forth, and then we used statistical average, okay, going from here to here to here, and then we find a relationship between microscopic quantities and macroscopic ones. This is how statistical mechanics work. Okay, now please don't forget that in the previous chapter we already introduced something about the pressure. Okay, the pressure of an ideal gas is related to its volume and its temperature. Remember that? Okay, in fact, you have P here, you have V here. I can move that V back over there so that I get PV equals 2 over 3 N K bar. But wait a minute, according to our previous discussion, PV equals nRT. What's N? N is the number of moles. This capital N is the total number of molecules. Okay, now how is small n and big N related? Well, this is number of number of moles. Each mole has Avogadro's number. So isn't this number of moles equal to the total number of molecules divided by the number of molecules per mole? That's Na, Avogadro's number, right? And then RT. All right. What I'm going to do is I'm going to single out this combination of R over Na. R is the so-called ideal gas constant, universal gas constant, that is, and Na is Avogadro's number. This R over Na, we have a special name for it. It is called the Boltzmann constant, Kb. Its value is first given in chapter 19, but now we have, starting from now, we're going to use this extensively. It's equal to 1.38 times 10 to the negative 23 joule per Kelvin. It is one of the most important fundamental constants of nature. We have so far studied two truly fundamental constants. One is the universal gravitational constant, big G. The other is Kb. Okay, in any correct formula involving gravity, you will have big G in it, whether explicitly or inexplicitly. In any correct formula about thermal physics, you're going to have the Boltzmann constant in it. The Boltzmann constant. Okay, so what you have here is this is Kb, right? This is Kb. On the one side, you have P times V. These are both macroscopic quantities. On the other side, you have Kb, which is very, very small, okay, because it has to do with molecular nature. And you have N, the number of molecules, which is very, very large. So they balance out. Okay, in fact, you take a look at the order of magnitude of Kb is 10 to negative 23. And the Avogadro's number, 1 mole, is 10 to the positive 23. So they cancel out very nicely. Okay, now, if we compare this expression with that expression, okay, and the number of molecules cancel out, we can then solve for K in terms of what? In terms of something we studied before but couldn't quite get the nature on, and that is temperature. Okay, it turns out that you can express the kinetic energy, the average value of the kinetic energy of an ideal gas in terms of its absolute temperature by equating this with that, and you come up with this remarkable expression, and that is K average equals to 3 over 2 Kb T. And let me emphasize on the fact that this is proportional to T, the temperature. Why is this so important? Because for the first time, we have some idea, we have some molecular idea of what temperature truly stands for. Okay, we all claim that we know something about temperature. Oh, it is an indicator of how hot or how cold something is. But these are superficial understandings. What is the true physical nature of temperature? Well, we have a first glimpse into it. It turns out that temperature is an indicator, or to be precise, it is proportional to the average molecular kinetic energy. Right? Look at this expression here. So this is the true meaning of what temperature really stands for. It gives an indication of what is the average kinetic energy per molecule. The higher the temperature, then on average, the faster the molecules move. In other words, the greater kinetic energy they have. The greater average kinetic energy they have. This explains why at the higher temperature, the pressure of a gas also increases, everything else being the same. Because on average, the molecules have greater kinetic energy, so they can strike the wall with greater impulse, and therefore, that increases the pressure. Okay, so not only did we figure out how to find the pressure of an ideal gas using statistical mechanics, we also have a very important byproduct. And that is, we, for the first time, understood the molecular nature, the molecular root of the quantity temperature. Again, temperature is proportional to the average molecular kinetic energy. So this is the so-called physical nature of temperature. And that also explains why temperature has no upper limits but does have a lower limit. Because look, after all, it has to do with kinetic energy of each molecule, right, on average. But you know, the kinetic energy has a lower limit. And what is that equal to? Well, 0, right? You cannot have negative value of kinetic energy, and therefore temperature has a lower limit, which is 0 on the Kelvin scale. It doesn't have an upper limit because there is no upper limit theoretically to the kinetic energy, but there is a lower limit of 0. So it's natural that the temperature has a lower bound, even though it doesn't have an upper bound. Now, we can use this formula to figure out some sort of average value of the molecular speed, because after all, this is 1/2 mv squared, right? So we can write 1/2 mv squared, average, of course, that equals 3/2 kT. Right? And from that, we can solve for v squared. So v squared average, that is, v squared average. What is that equal to? Well, that is 3 kT over m. Okay, now we're not interested in squared, so I'm going to take the square root. So you take the v squared, average it, and then you take the square root. What is that equal to? That equals to 3 kT over m. Let me ask you, are we calculating the average speed? No, we're not. Because when you calculate average speed, that should be v1 plus v2 plus v3 blah 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 divided by the total number of molecules, right? What we're doing here is we're averaging v squared first. Okay, so we're doing v1 squared plus v2 squared plus v3 squared and so on and so forth divided by n number of molecules, and then we take the square root of the whole thing to bring back the units to temperature. I mean to speed. Okay, so this is not quite the same as average speed, but it should have the same order of magnitude. What is the name for this quantity? We call it RMS speed. VRMS. What's RMS mean? Okay, R means root, M means mean, and S means squared. So what you do is you square it first, that's S, and you take the mean value, that's M, and then you take the square root, that's R. Okay, RMS speed. The RMS speed has the same magnitude as the average speed. We can find some numerical value now. It turns out for any ideal gas, the RMS speed of that gas depends on only two quantities. It depends on the temperature of the gas and the molecular mass of the gas. So suppose I have two tanks of gas at the same temperature, say hydrogen and oxygen. Obviously, the oxygen will have a slower value of average speed because its mass, the oxygen has greater mass than the hydrogen. Okay, so among all the gases, hydrogen has the fastest average speed because it has the smallest mass. Why are we interested in RMS speed? Well, there are at least two reasons. One is the RMS speed is pretty close to the average speed of the molecular motion, and that sort of have to do with the speed of sound in that medium, don't you think? Because how does sound propagate? Don't we need molecules to collide with each other to pass on information? The only way for molecules in a gas to pass on information is by colliding with each other, right? So the faster they can collide with each other, the faster the sound wave can propagate. So we can expect the molecular average speed to be comparable with the speed of sound in that medium. Okay, now we can do some calculation for a certain type of gas, say oxygen or hydrogen or whatever, at a certain temperature, say room temperature, and we can find the RMS value. Okay, and what you find is on page 645, table 21.1, and here they list a number of gases, hydrogen, helium, water vapor, and so forth. It turns out the RMS value, of course, is the greatest for hydrogen at the same temperature, is 1902. And you look at these other values, they're usually several hundred meters per second. And indeed, you see, this is comparable with the speed of sound. Say the speed of sound in air is, say, 340 meters per second. The closest one I can find, oxygen. Okay, oxygen 478 meters per second for RMS. So indeed, they're comparable with each other. Another reason I want to discuss that is because imagine you have a planet. Okay, this planet, in order for life to be able to sustain, you need an atmosphere. An atmosphere is, of course, filled with gas molecules. Each gas molecule can move with a certain speed. The question is, if the temperature of this atmosphere is high enough, then wouldn't it be possible for this gas molecule on average to acquire enough speed so that its RMS speed exceeds the escape speed from this planet? Now, if that is the case, of course, even if you have an atmosphere to begin with, when the temperature rises, the gas molecule will move fast enough on average. They will have enough energy to escape, so that you're going to lose that atmosphere, right? So the atmosphere cannot be sustained. So in other words, let us compare the RMS speed of gas molecules with the escape speed from a certain planet. Let's use the Earth as an example. Okay. For the Earth, VRMS for air, several hundred meters per second. Okay, let's use oxygen as an example. All right, actually, for oxygen is at 20 degrees. That's about room temperature, 478. Let's say 500. Okay, 500 meters per second. Do you still recall the escape speed from Earth? Okay, what's the minimum speed it takes to totally get away from the Earth's gravitational pull? That is 11.7 kilometers, or 11,700 meters per second. You see, this is far greater than VRMS. In other words, the Earth, the gravitational pull of the Earth is strong enough that it is much greater than the average speed of an air molecule in the atmosphere. This is why the Earth is capable of retaining a stable atmosphere. Such is not the case for the Moon. Okay, for the Moon, the RMS speed at, say, 20 degrees temperature is actually less than the escape speed from the Moon, because the Moon, the gravitational pull is a lot less than the Earth. So this is why the Moon does not have an atmosphere, which is why life cannot be sustained on the Moon without any assistance. So it is interesting for us to figure out this relationship between V escape and VRMS, and this further explains why we have a stable atmosphere.